mentioned this briefly in my runtime presentation, but Groq has, in the last, I'll say 9 months, Groq has spent a lot of time working on beefing up our runtime, so to speak, to run with LLMs. So I thought it would be kind of interesting, as a lot of you are kind of AI researchers and might not be, interacting with the lower level bits and bytes of our runtime, to kind of tie the work Groq's been doing with our runtime back to how you can run an LLM on your Groq hardware. So with that said, kind of this slide, nothing new, just a bunch of headlines talking about how transformative LLMs are and how they are the next kind of revolution in computing. And there's this huge interest in LLMs, a wide range of use cases, all the way from code assistants, chatbots, scientific research, a ton of things. So Groq is well aware of this, and we've been working on LLMs. And maybe specifically, I believe a lot of you folks at A&L do a lot of scientific type research. So LLMs in science are enormous, for protein string generation, or language and scientific domains. LLMs are heavily used in science and research these days. And Groq LPUs are highly suitable for running LLMs for a couple of different reasons. One of them is that are these large matrix multiplications that are part of a transformer architecture are really effectively mapped to our MXM block in the Groq LPU. So I believe Andrew Baitar yesterday gave an overall architecture discustion of the Groq LPU. And so we have a lot of functional units in our chip that map very well to a lot of the matmuls that need to be done for running transformer-based models. Additionally, LLMs are kind of a serial problem. When I'm giving you this presentation, I haven't already thought of the 50th word I'm about to say. I think of the 48th, 49th, and then the 50th word. And so this kind of sequential nature of LLMs requires a lot of weight loading, which is very, very costly in GPUs, where you're reading to and writing from HBM all the time, loading and kind of unloading your weights, versus something that the Groq LPU can do very, very quickly and very power efficiently in the SRAM baked into the chip. And so I kind of like this analogy, but you can think of us running LLMs across all our Groq LPUs as one giant assembly line, because the chip is fully deterministic, and we have cycle by cycle granularity as to where data is, not only across one Groq chip, but across 72 chips, a Groqrack, or 144 chips, 2 Groqracks. We can scale up very, very effectively, and it's that strong scaling we have that allows us to demonstrate these incredible high performance metrics when running LLMs. I'm kind of rehashing a bit of what Andrew said from his presentation yesterday, but there's no reactive hardware components, and no arbiters, no queues, and this allows our compiler to quickly reason about data movement without these expensive cycle accurate simulations that you need to have in GPUs, which allows us to just split up a model across multiple LPUs and run tokens through it at incredible performance numbers. So I kind of mentioned a little bit about this briefly, but how is an LPU processing different from a GPU? Most of the time, GPU's processes, or most of the GPU time or energy, is spent paging weights and KV cache in and out of their HBM. One sec, this is maybe a better slide. It has some animation, but most of the GPU cycles are spent reading and writing to HBM, these really high intense memory read and write operations. And those are highly inefficient. There's a high HBM access latency where you just add on, a microsecond for each read or write. And you are also spending a lot of power to do these reads and writes and move data from HBM to your core compute and back and forth. There's also very slow asynchronous communication through GPU switches, which can result in high latency as well. And overall, GPUs have an expensive bill of materials, and there's always supply concerns with HBM, like where are you going to get HBM from, as well as most GPUs require like exotic packaging technology, like TSMC's chip on wafer on substrate technology. So this makes GPUs difficult to scale for performance reasons on the GPU and kind of supply chain reasons. But the Groq LPU doesn't have these kinds of problems. We're not relying on HBM at all. We're purely just a single chip that can scale up very strongly due to our determinism. And we aren't reading to and writing from a ton of weights in and out of memory. We have all the weights stored in SRAM, which is orders of magnitude faster and more efficient than HBM. So this allows us to just get amazing performance numbers, as well as very like a reasonable amount of power burn when processing tokens for when running an LLM. And so these are just a few diagrams of how you can think about LPU performance versus GPU performance. Where on one side you have kind of, forget it. And yeah, that should be it, I believe, for me. One other thing, maybe about 9 months ago now, I created a little script for the ANL engineers that showed running Llama 2 7 billion on the Groqrack that is in the ALCF compute cluster. This is not the best fidelity video, but it was possible to run LLMs on ANL's one rack, 6 to 9 months ago. And we're only getting better and being able to further quantize and run our models more efficiently. So now you can run Llama 3 8 billion on a single rack as well at incredible performance. I don't think these slides are in here, unfortunately, but if you go to artificialanalysis.com, you can see the incredible performance we're getting on Llama 3 8 billion or like Llama 3 70 billion, Mixtral, mixture of experts, and models like that. So that's all I have for this presentation. And with that, I will yield back to Hatice.